Jai Hind everyone. I, Suvarna Mujumdar, Assistant Professor in Electronics and Communication Departments, welcome you in a lecture on Assembly Language Program for 8085 Microprocessor. In this lecture, we are going to discuss about different assembly language programming program so that we can understand how we can write a program for 8085 and what is the assembly language programming. As we all know, microprocessor is a machine, electronics device, or it is a programmable device which can understood only the data in the form of 0 and 1. But we have to write a program so that it can perform some task. This program either we can write into a binary language, that is 0101, but it is very difficult for a programmer or user to understand that code. So we can write our program in a text-based language and something which can be converted into machine code. So we write the program in assembly language, which is half text-based and half of the data will be in numeric numbers. And assembler will change the data so that microprocessor can understood the program. So the assembler will convert our written program into a machine program. So now we are going to write a program for 8085. So here we can see that there are mnemonics. Mnemonics means the assembly codes which we are going to write for assembler, and assembler will convert that opcode into a hex code. As any instruction consists of two parts, opcode and operand. So each instruction will either have a opcode and operand, like our instruction, we know one instruction MVI A, 34H. So here MVI is an opcode and 34H is the operand. So assembler will convert this MVI into a machine code, and a particular hex code will be stored in the memory location, and then the 34H will be stored. Now we have taken an example that we have to count a number of ones in a particular data, and we will display that result. So this is our first objective to write a program. So first of all, we will see that from which location or what is the place from where we have to read the data, or then we have to count the number of ones in particular data. So let's take an example. So let us take 9000 will be the location from where we have to read the data, and then we have to count the number of ones in that particular data, and then we have to store the result at 9001 location. So first of all, we have to read the data from 9000H location, and then we have to count the number of ones, and we have to store that number of ones in some register, and then we have to display that result. So first, the instruction that we have to read the data. So we will write LDA 9000H. So when this instruction will be executed, the data which is stored in 9000 location will be stored in the accumulator, and now we are going to initialize one register B so that we can count the number of ones at the data in this 9000 location. So let us take an example that in memory at 9000 location there will be some data, X data, and this data we will be getting it in the accumulator, and B register we will initialize at 0. Now as we know that our data which is stored in 9000 location is of 8 bit, so we have to initialize a counter so that we can count all the 8 bits. So we can initialize the counter with 08H. So C, mostly we will see C register as a counter register. Now we will rotate our data so that the content of accumulator get rotated, and we can get the first value in the register in the carry flag. So we will use RAR instruction, rotate right through carry. So first data byte will be in carry flag, and now we will see whether carry is generated or not. So if carry is not generated, we will jump to next, and if carry is generated, means carry is high, we will increment our B register. And if carry is not generated, means the content is 0, we will just decrement the count by 1 so that 1 data is stored, and this instruction has to be repeated till it reaches to 0. So we have to rotate it again. So we will go back to jump loop, and now once all the data, all the 8-bit is rotated and reached to the carry flag, it will come out of the loop, and now we will store the content of B into A, and then we will use STA 9001H to store the result. Okay, let's see how it is going to happen. That the content at 9000, let us take this X value will be 39. So if we write 39, it is 00111001. Now if we rotate the data right, the data should be rotated right. So this data will come to C carry flag. Okay, and the first data will become to carry flag. First data bit is 0. So carry is not generated. So it will not increment B register. It will go to D. Now D becomes 7. In this way, this loop will be executed, and we will get a value, that is number of ones. That is here in this, for example, it is having 4 ones. So the B value will be 4, and then that B value will be stored in accumulator, and we will store this result at the 9001 location by the last instruction. So this is a generalized program where we can write a program for any of the number. Now we have to just change the data at 9000 location, and we can count the number of ones for that particular location. Now we can go for the next program. Now in this program, we have to transfer 10 bytes of data from one memory location to another location. So let's take an example that we have to transfer 10 bytes of data from 4000H location to 6000H location. So we need two pointers, one which is pointing to 4000 location and another pointing which will be pointer to the 6000 location. And we need a counter which can count that we have reached the 10 data byte is transferred from one location to another. So let us take, we know that LXI H will be the first HL pair will be the one pointer register which we will be using as a source pointer register which will point to the 4000 location, and we will use D as a next pointer, or you can say the destination pointer. So first of all, we will initialize two pointer register, HL pair for 4000 and DE pair for 6000. Now we need a register which is used as a counter register. So either we can choose C or we can choose B as per our wish. So I can choose C register and I load it with the value 0A because I want to transfer 10 data byte. If you have to transfer 15 data byte, you can make it 0FH. So depending on the number of data byte you have to transfer, you can initialize the counter register. Now first we have to read the data from the source location and then we have to transfer that data on the destination location. So just check here. This is our 4000H location, 4001, 4002. Like this we have 4009. Similarly, we have 6000 location, 6001, 6009. So here some data is there. Okay. So we have loaded the HL pair. So HL pair is pointing to this location. 6000 will be pointed by DE pair, and C register I have loaded it with 0A. Till now we have done this. Now we have to read the first data. So we can read the data by instruction move A comma M. When this instruction is executed, the content of A register will be 37. The first data will be in accumulator. Now this data has to be transferred and copied to 6000 location. So for this we will use an instruction STAXD. So this instruction, by using this instruction, the content of accumulator will be stored at the location whose address is pointed by D register. Now the first data is stored, 37 is copied. Now we will increment our HL pair. So now HL pair will point to 4001 location. Then we will increment D. So D will point to 6001 location. Both are incremented. One data byte is transferred. So we will decrement the counter DACRC. Now DCRC, the counter will be decremented. And the counter value becomes 09. Counter is decremented, and now counter is not went to 0. So we will go for loop. So we will go back again, and now it will read the next instruction, next data. So now the data from 4001 location, it will be copied to 9A. (9A) will be here, STAXD, and it will be stored here. Increment, next line. Now this loop will be executed, and once the 10 data byte is transferred from 4000 location to 6000 location, the DCRC, decrement C, it reaches to 0, the loop comes out, program counter will be out of this loop, and we will stop the program, that is RST 5. So in this way we can write a program so that microprocessor can communicate or transfer 2 data bytes from one location to another location. Next, now if we have to multiply 2 data and 2 8-bit numbers we have to multiply. In case of microprocessor 8085, we don't have such an instruction which can multiply 2 data. We have addition instruction and we have subtraction instruction. So the concept which we are going to use in case of multiplication, that is repeated addition we have to use, and we have to multiply 2 8-bit numbers using 8085 programming. So multiplication, for multiplication, we need 2 data bytes. Let us take an location 4000 and 4002, 4001, 4000 and 4001, where we have multipliers A and B, suppose, and we have to multiply these 2 numbers. So first of all we have to read the numbers, then we have to go for repeated addition. So first we will read LDA 4000H. First data byte will be in accumulator. Now we have to get second data byte again in the processor from memory. So first we will store this data into E register. You can choose any other register. Then we will take another, we will read another data, and before that we will make D register as a 00H, so that only the data, the content 8-bit data in the E register, and there is no data in the D register because we need the DE pair. Then we will read second data byte LDA 4001. So our first data byte, first number is in E, second number is in accumulator. Okay. Now we will go for this number we will store in C register. Okay, and we will go for DAD instruction that will add two 16-bit numbers so that we can have the multiplication if the result is more than 8-bit. So we will go with LXI-H. Okay. Then we will go with DAD-D. So first number is in D register, another number is in C register. The C data will be, this data will be act as a counter. So we will go for repeated addition, that we add A B times. This is the concept. So suppose we take 9 and we get 4. So we add 9 4 times. So C is as a counter and the data 9 is in DE register. That D, it will do, this instruction will add the content of HL pair with DE register and store the result in HL pair. Now first addition is confirmed, we decrement the counter. Okay, jump if not 0, back, we will again addition. Then if we got the result, then we will store that result to next location 4002H. Let us understand once again how it is going to proceed. Let us take an example that A is equal to 9 and B is equals to 4. So first of all, when LDA 4000 is executed, the content of A register will be 9. This 9 will be transferred to, this instruction will transfer this 9 to E register. D register is 0. So we will see that the content of DE register will be 00 and 09. From this instruction, the content, second instruction 4001, it will be stored in accumulator. So now a content of accumulator will be 3 and this 3 will be stored in C register as a counter. So this instruction, from this instruction C register we have value 4. A is A equals to 4. So now C equals to 4. Now LXI H pair is having 0 0. So from this DAD D instruction, the first 0 will be added with 9 and result will be stored in HL. First addition is performed. So C will be decremented by one value, C becomes 3. Next addition 9 plus 9, again C will be decremented by 1, 2, again 9 plus 9, third time, 1, fourth time, it will become 0 and we will come out of loop. The result after addition, it will be stored in HL pair. So from this instruction, store the content of HL pair to 4002 location. The data will be copied to the consecutive location. So content of H and L will be transferred here and we get the result. Why we use this DAD instruction? Because we see that whenever we multiply two 8-bit number, the result will be greater than 8-bit. So result may be in the range of 16-bit. So we use HL pair and DE pair for addition of greater than 8-bit number. You can use repeated addition with 8-bit register also, but in that case you have to look at for carry. For each of, after each addition you have to look at for carry. But if you go with that instruction, you don't have to look after about the carry and you can proceed without carry also, because that instruction will do the needful for you and it will look after the carry for each addition. Okay. Now let us look for the content, one more program that is all about delay subroutine. So if we have to generate a delay of 1 millisecond, how we can write a program? So we have to write a program to generate a delay of 1 millisecond. So we have to first find out what is the crystal frequency of our processor, or we have to find out the clock frequency, crystal frequency, or we can say the clock frequency of our microprocessor. So let us assume that our crystal frequency, or you can say the clock frequency, crystal frequency is 6 megahertz, and as we know 80-85, the clock frequency will be the half of crystal frequency, so it will be 3 megahertz. Now we can have a generalized delay program, and from that generalized delay program we will generate a delay of 1 millisecond. So how we can generate a delay program? So the basic concept is that we will initialize one of the register as a count with a count value, and we decrement that register till that count reaches to 0. The microprocessor is executing these instructions in a loop, and the time taken by microprocessor to execute these instructions will constitute a delay of that particular time, and that delay we will count as a 1 millisecond or 2 milliseconds. So the count value will decide the execution time. So just we will have a generalized program that if we write MVIC comma count, I just don't know about the count value. And we will decrement this DCRC and jump if not 0 to back. So these are the 3 instructions as my delay program. This is a general delay program. Now the number of T states required to execute these instructions will constitute the delay. So let us know that just count it and revise it, that MVIC comma count. This instruction is a 2-byte instruction, and it has 2 machine operation. One is memory read, opcode fetch. The first memory operation is opcode fetch, and next memory operation is memory read. So to execute this instruction, it requires 7 T states. 4 for opcode fetch and 3 for memory read. Next instruction is decrement C. It is a 1-byte instruction. So here only the opcode fetch. So we will need only 4 T states. Next instruction is JNZ loop. So in JNZ loop, we can have 10 T states and 7 T states. If the loop is means if condition is not satisfied, this jump if not 0. So if this condition is satisfied, jump if not 0, then it will take 10 times, and if C the content reaches to 0, that is jump if not 0 is not valid, then it will take 7 T states. So here normally it takes 10 T states, and for last execution it will take 7 T states. And whenever we call any subroutine program, the last instruction that is called, we have a return. So here in case of return, again we have 10 T states. This is the one which is having more T states. So from this T states counting, we will find the value of this count for 1 millisecond. So the program, or we can say how we can calculate this will be like this. We have loop, mathematical calculation will be loop. The total we have, this loop is executing repeatedly. Okay. And for this we can say 10 plus 4. This is executing for count times. Suppose count is 5, then this 14 T states will be executing for 5 times. And then the remaining 7 and 10. This 7 and 7. This 14 T states. It will be executed only once. So we will write it 14. So time is 1 millisecond. So we will have this is equals to 14 into count plus 14 t, and from here this 1 by 3, so we will have count value is equals to 1000. So we will count this and we will found that this count value, and we will substitute this count value at this location, and we will have a delay program. Now, if we have to add two 16-bit number, how we can write the program? So for addition of two 16-bit number, we will have to read the data from two memory location, and then we will have to add these two 16-bit number. And for 16-bit addition, we will go with lower byte addition first, and then we will go for higher byte addition. So if we have to read two data bytes from a location, the instruction we will going to use to add 16-bit to just write a program for 16-bit addition. We will use HLLD, load HL pair with the data. So if we use for 2050H will be the location where we have first 16-bit data, then 2050 and 2051H. From there we will have a data on HL pair. Then we will exchange this data XCHG, and we will store this data into DE register. So our first content, first data byte of 16-bit will be stored in DE register. Then again we will go and we will read HLLD 2052H location. 050 and 501 will be 51 will be the first data 16-bit data, then 52 will be the second. So now HL will be having second data byte. Now to add this data, we will first move E register content into accumulator, and then we add L. Okay, so content will be added. So just have a look how we are going to proceed. Our data our 2050, 2051, 2052, 53. So we have data 3A, 40, 25, 28. So this is our data. So this is our 16-bit data. We store this into, first we will get it into HL, then we will exchange it. So now DE will having this data. So D register will having 3A and D register will having 3A, E register will having 40, H is having 25, L is having 28. So this is our data. When we write move A comma E, so A is having now 40 and add L. So this 40 will be added with 28. Okay, and the result will be stored in the A register. Now move A comma E, E content will be in A, add L, content will be in accumulator, and now we will move this result to A register only, so that the lower byte data result will be in L register. Now we will check, we will take the data from D, that is higher byte, we will store it into accumulator, and we will add hash to it. Okay. Now, while doing this addition, we will go with ADC. So, if a carry is generated at earlier time when we are going to add 8-bit number, then that carry is transferred to the higher side. So, when we are having this addition between these two numbers, if carry is generated, then that carry will be transferred when we are having this addition. So, the result will be in H, and now we will store SHLD, and we will go with 2053 location to store the result. So, in this way, we will have a program for 16-bit addition using 8085 only. Okay, so we have studied 4 to 5 programs in which we have studied about delay program as well as the addition, multiplication in 8085. This is all about the assembly language programming of 8085. Thank you.